Good morning. Today, I'd like to review the introductory material about vectors and systems of equations that we've been looking at recently in Mathematics 1730. In most of what we've done so far in mathematics, we've primarily been concerned with things that can be characterized with a single number, such as 3 kilograms, 4 meters, 120 volts, and so on. Quantities like that are called scalar quantities to distinguish them from the vectors, which we're about to talk about. By way of contrast, a vector is a quantity that you can't describe with just a number, but also you have to give a direction to it as well. Examples of those things include forces, electric fields, magnetic fields. In each of these cases, for each point of the plane in our case, or 3 dimensions more generally, there's going to be an arrow that points in some direction or the other and has a certain length. To begin with, we'll think about the simplest possible case, which is the vector from one point of a plane to another point. For example, if I had 2 points in the plane, P and Q, and I draw the arrow from P to Q, I'm going to call that the vector from P to Q. The symbol that we'll use for that is this symbol. The arrow reminds me that I'm talking about a vector, not a scalar quantity. If I had started at Q and ended at P, we'd call that vector the vector from Q to P. As it stands right now, there is some wiggle room here. We said that a vector was a quantity that has both a length, the length of the arrow, and a direction, the line upon which this arrow points. There are lots of arrows that have the same length and point in the same direction, though. For example, all of these arrows have the same length and point in the same direction. By same direction, of course, I mean along parallel lines, not pointing towards the same point or anything like that. Strictly speaking, these are all not the same vector because they start at different places and also end at different places. So it wouldn't be quite right to call these vectors equal to each other. Instead, we'll say that they are equivalent to each other. A vector is a quantity that has both length and direction. We'll create a symbol to represent the length of the vector. It's kind of like the absolute value symbol, except it has two vertical lines instead of just one. We call this the length of the vector from P to Q, or the magnitude, or the norm of the vector from P to Q. Likewise, if I decide to give one of these equivalent vectors some name of its own, I'll call it vector v. The distance from the starting point, the initial point, to the ending or terminal point is the magnitude of vector v. It is literally the distance from this point to that point. You'll notice that up to this stage I have not talked about an x-axis or a y-axis or any such thing. We'll see how that works into this in a minute. If I think about this in terms of coordinates, I need two numbers to tell me where P is, the x and y coordinates of P, and I need another two numbers, the coordinates of Q, to tell me the entire situation, though. If I decide to go ahead and set up the usual kind of XY coordinate system, though, there's something else that I can do. Out of all of these equivalent vectors that have the same direction and magnitude, one of them is going to have its initial or starting point at the origin. We'll say that a vector is in standard position when that happens. As an example of what I'm talking about, I'm going to think of having a vector from P to Q. P is the point where x is 3 and y is 1. Q is the point where x is 7 and y is 5. This arrow is what I mean by this quantity. There are an unlimited supply of equivalent vectors to this vector. One of them has its start point at the origin. To figure out what I should draw in, let's think about this for a moment. I could imagine physically starting at point P and then doing something to the coordinates so that I end up at point Q. Here, I started off at x equals 3 and ended at x equals 7. I've added 4 to the coordinate. 3 plus 4 is 7. Here, I started off at x equals 1 and then ended up at x equals 5. 5 is 1 plus 4, so I also have to increase the y-coordinate by 4. If I were to take a vector that's equivalent to P to Q, then what I would do is I would start wherever it is I start at, increase the x-coordinate by 4, and increase the y-coordinate by 4. This leads us to our little formula that says the way that we're going to find the coordinates of this endpoint is the coordinates of the point at the end, the Q, minus the coordinates of the point at the start, P. 7 minus 3 is 4. 5 minus 1 is also 4. If I have the vector that starts at the origin and is equivalent to vector P to Q, the endpoint will be x equals 4, y equals 4. This is what we mean when we say that we're looking at the vector in standard position. More generally, if I have some vector and I look at its equivalent vector in standard position, it'll go from the origin out to some point. I'm going to call this vector v. Here, when I use the parentheses, I'm talking about the end point, the point where x is v1 and y is v2. When I use the bracket notation, the sharp angle notation, I'm referring to the entire arrow that starts at the origin and has v1, v2 as the x and y coordinates of the end point. These numbers, v1 and v2, are called the components of the vector. This form, naturally, is called the component form of the vector. Given 3 points in the plane, P, Q, and R, I can form the vector from P to Q, P to R to Q, Q to R, and Q to P by doing the end minus start idea. To find the components of vector P to Q, I look at the coordinates of the end point, Q, 5, and 6, and I subtract away the coordinates of the initial spot, P, 1, and 3. I do the arithmetic. Vector P to Q has components 4 and 3. Likewise, you can calculate the components of any of these other vectors. Given two vectors, u and v, I can think of selecting a vector that's equivalent to u, one that's equivalent to v, that have a common starting point. Then I can think of having a copy of vector v, a vector that's equivalent to v, that has its initial point at the terminal point of u. Also, I can think of having a representative equivalent vector for u, except this one doesn't have its starting point here, it has its starting point here instead. Since this is parallel to that, and these two vectors have the same lengths, and since this vector is parallel to that one, and this vector and that vector have the same length, this is a parallelogram. In terms of geometry, we're going to define the vector u plus v to be the vector that goes from the common starting point of u and v out to the far end of the parallelogram. We'll see how to calculate this sort of thing with numbers shortly. In the parallelogram picture, set it up as before. U and V have been set up to have a common starting point. Set up the picture as before. U and V have a common initial point. From the end of V, attach a copy of U. From the end of U, attach a copy of V. And based on our end minus start idea, it's going to turn out that the vector that starts here and ends there should be called u minus v. On the other hand, the same kind of thinking tells me that if I start at this point and end at that point, then a reasonable name for this vector is v minus u. The third kind of vector arithmetic operation that we can do is multiplying a number by a vector. If the number is positive, then the number times the vector is going to be a vector that points in the same direction as the original, but the length will be different. For example, if this is a representative of vector u, this will be a representative of a vector named 2 times u. It points in the same direction as u, except it's twice as long. If the number I multiply by is negative, it's the same sort of thing, except the direction has been reversed 180 degrees. So if this is u, negative u will be pointing in that direction. For example, negative 3u is a vector that's 3 times as long as u is, but points in the diametrically opposite direction. Other than geometry, very often we would like to do vector arithmetic in terms of numbers, just as we do in ordinary algebra. Imagine that you have a vector u in standard position. The endpoint of u has coordinates u1 and u2. Vector u is bracket u1, u2. Likewise for vector v. Let's draw in the parallelogram that we were talking about a moment ago. On the other hand, if I start at the origin and go out to this point, the x and y coordinates of the endpoint are the components of this new vector. This new vector is u1 plus v1 for the first component, and u2 plus v2 for the second. Looking at this, I don't feel too bad now about our definition for addition in terms of the parallelogram. If u and v are vectors, then the following equation is true. So if I have the component form for two vectors, and then I want to find the sum of the two vectors, then this is an easy thing to do. On the other hand, this point has coordinates v1 and v2, while this one has coordinates u1 and u2. If I find the components of the vector that starts here and ends there, we will use our end minus start idea. The end has coordinates u1 and u2. The start has coordinates v1 and v2, so the end minus start thought produces this vector. Comparing against what happened before, there's a natural name that we would give to this vector. We will call it u minus v. In a very similar way, if I form the vector that starts here and stops there, then we'll be able to figure the components of that one out also. Doing the end minus start thing again, we see that we have the components of v with the corresponding components of u subtracted away. Obviously, the name that I'll give this vector is vector v minus vector u. When we form this standard parallelogram, one of the diagonals, the long one, tells us u plus v. One of the other ones, this one, tells us u minus v, and this one tells us v minus u. If this were ordinary algebra, v minus u would be the negative of u minus v, so we can think of it that way as well. We will define a number times a vector in the following way. For example, if you had a vector u with components u1 and u2, so this x-coordinate would be u1, this y-coordinate would be u2, then to obtain the vector 2u, I'll just take both of the components and multiply them by the 2. 3 times u would be 3 times u1, 3 times u2, and so on and so forth. We'll see shortly that if you multiply a vector by a positive number, what you get is a vector that points in the same direction as the original, but is a different length. In this case, 2u will turn out to be twice as long as u is. 3u will turn out to be 3 times as long. If I take a negative number and multiply it by u, I get a vector that points along the same straight line that u points along, but in the opposite direction. So negative 3u would be a vector in standard position that starts at the origin, travels out a distance 3 times the length of the u vector, but in a direction that is 180 degrees opposite. Typically draw my triangles and vectors as though they point off into the first quadrant. That's just for convenience sake. The same kind of ideas will work even if that's not so. If I have a vector u, its first component is u1, its second component is u2, think about the angle alpha that the vector makes with the positive x-axis. We have 3 things going on for us. Firstly, there's the Pythagorean theorem. Secondly, there is the definition of sine alpha and cosine alpha. I want to see if I can write down yet another form for these vectors that we're talking about. The long side of this right triangle has the same length as the arrow that starts at the origin and ends at the point u1, u2. This distance is the magnitude or norm of vector u, so in my triangle I'll write it that way. This distance across the bottom is u1 if u1 is positive, negative u1 if it's negative. Likewise here, the possible negative signs make no difference because I'm going to end up in the Pythagorean theorem squaring those numbers anyway. The norm of a vector is the square root of the sum of the squares of the two components. On the other hand, cosine of alpha is adjacent u1 divided by hypotenuse, norm of u. Sine alpha is opposite alpha, u2, divided by the hypotenuse. You can rearrange these formulas. This one tells me that the first component of u number 1, is the length of u times cosine alpha. On the other hand, this one tells me that u2 must be the length of u times sine alpha. Vector u has components magnitude of u cosine alpha, magnitude of u sine alpha. By the way that we've decided how to multiply a number by a vector, though, I can split this up some more. So yet another way I can think about vectors is a vector, which is an arrow, is a number, the length of the vector, times another vector that has cosine and sine of the same angle as its components. It's not difficult to show that the magnitude of a cosine sine vector like that is always 1. So this says that u is this number, which tells me the length of u, but has nothing to do with the direction, times this vector that tells me the direction, but since its length is always 1, tells me nothing about the length of the vector u. This is sometimes called the polar form. We can now easily apply all of these ideas in order to solve the following type of problems. Suppose that I have three vectors, a, b, and c. The length of a is 8, and a makes an angle of 27 degrees with respect to the positive x-axis. The length of b is 10, and it makes an angle of 330 degrees with respect to the positive x-axis. And vector c has length 23 and makes an angle of 145 degrees with respect to the positive x-axis. I'd like to find the vector sum a plus b plus c, also known as the resultant. After finding that, I'd like to be able to tell you the length of that vector, the length of vector a plus b plus c, and also I'd like to tell you the direction that that vector is pointing in. Remembering that we can express a vector as the length of the vector times its cosine sine vector, this information tells me that a must be the number 8 multiplied by the vector with components cosine 27 degrees, sine 27 degrees. Likewise, b is 10 times vector cosine 330 degrees, sine 330 degrees, and c is 23 times the cosine sine vector that goes with 145 degrees. To make this a little bit easier to calculate, I'm going to use the idea about number times a vector here. It's better to write it like this because when I add a plus b plus c, I'm going to have two components, two numbers that go in the first and second position in the vector. The first number is going to be that number plus that number plus that number. If I wanted to, I could sit down and figure those numbers out as decimal numbers using my calculator, and then type them back in to add them up, write the answer down, and call that the first number in a plus b plus c. Likewise, I could figure that number, and that number out. As we can clearly see, we are in degree mode. My document camera seems to think it knows better than we do about when it should focus and not focus. So, pardon the continuing joke. As you can clearly see, I'll just take this number and add it to that one and add it to that one. 8 times cosine of 27 degrees plus 10 times cosine of 330 degrees plus 23 times cosine 145 degrees. So 8 cosine 27 degrees, 10 cosine 330, 23 cosine 145 works out to be negative 3.052. I'll keep that many digits. 05219, that is. To get the second component, I have to do the same calculation, except instead of 8 cosine 27, 10 cosine 330, and 23 cosine 330, pardon me, 145, that is. I need to do the sine instead of the cosine. I'll just do this in a straightforward way. 8 times sine of 27 plus 10 times sine 330 plus 23 times sine 145 degrees. This works out to be 11.82 some odd. 11.824182. We now have the component form of the vector a plus b plus c. I'd like to do two other things. I'd like to find the length of the vector a plus b plus c, and also I'd like to find the direction of that vector. As I'm fond of saying, it never hurts to draw the picture. The first component of a plus b plus c is a little bit more negative than -3. The second component is a little bit less than 12, so a little bit more than -3, a little bit less than 12. This vector points off into quadrant 2. This is where we have to be careful. If I try to use the inverse sine or the inverse tangent just directly on this, I'm not going to get the right answer, because inverse tangent and inverse sine cannot produce angles in the second quadrant. I could try doing something with the inverse tangent and the 180-degree trick, or I could look at what I've got and say, this angle alpha is between 0 and 180 degrees. The inverse cosine can get me that kind of angle. When I square -3.05219, the negative sign goes away. Be sure to include the negative sign inside the parentheses before you square, or you could just leave the negative sign out because it's going to go away anyway. Square these two numbers, add them together, do the square root, and we find out that the length of this vector that we're looking at is 12.21176. Just previously, we've mentioned that a vector is the length of the vector times a cosine sine vector that goes with it. We're going to take advantage of that fact. Because of the way that we said we're going to do numbers times vectors, if I have 12.21176 times this number comma, that number. If I were to simplify that, this would be this 12.21176 number times this first bit. The 12.21176 would cancel out, giving me the first number in a plus b plus c, and likewise, this number times that number is 11.824182. Because of the way we figured out that lengths and angles can be determined, since the 12 number is the length of a plus b plus c, the rest of it must be the cosine sine vector for a plus b plus c. Sine of alpha is that number. I do not want to try to take the inverse sine of that number to figure that angle out, because inverse sine can't produce this angle. Cosine alpha is negative 3.05219 over the length of a plus b plus c. Alpha is in the range 0 to 180 degrees. The inverse cosine can produce that angle, so that's the one that I want to go after here. Doing the inverse cosine of this number ends up telling me that the alpha needs to be 104.47 degrees. If you look at the picture, that is consistent with this calculation. The actual alpha is obviously bigger than 90 degrees, but not as big as 180 degrees. Originally, I was going to go on and put the systems of linear equations bit in this video as well, but I see it's getting a little bit on the long side. So I'm going to split this up into two videos. One, over the vector material. Secondly, systems of equations. I'll get this edited and put up on YouTube tonight. Keep an eye out for the system of equations bit. In the meantime, I hope everybody's having a good evening. I'll talk to you again soon.